Okay, so what we're going to look at here is an idea or an application of integration. I remember when I was first introduced to integration, the maths teachers weren't very good at actually explaining, as with many things in maths, what you actually use it for. And I still remember a corridor conversation even now where we coined the idea that all integration was useful for was finding the fourth dimensional space under the three-dimensional object, which we decided was the fourth dimensional space under C for the urinal. 15, 16 years old, seemed funny at the time. Anyway, what we're going to look at is an application of integration that you're familiar with from A-level physics, or at least the outcomes, but not necessarily where it comes from. So what we've got then, you should be comfortable with the idea that dv by dt is equal to acceleration. The other way you might have seen is delta v divided by delta t is equal to acceleration. So change in velocity divided by change in time is equal to acceleration. And in maths, you'll have moved from writing delta v divided by delta t into dv by dt. Now in maths, they are quite good at teaching you how to integrate. So I want to integrate this with respect to time. So to integrate with respect to time, I get v, and that is going to be equal to, well, a times by t plus some form of constant. Exactly the same way that you would have written dy by dx is equal to a, and you'd be quite happy integrating that up to y is equal to ax plus a constant. It's the same thing, slightly different letters. Now, this doesn't look particularly surprising, but if we look at it and actually rearrange it ever so slightly just to make it a bit easier, so I've got c plus at. Now I know if at time t, I know my velocity is going to be equal to, my velocity at time t is going to be equal to my initial velocity. So what I actually know, if time t is 0, therefore I know that c is equal to u. So what I've actually got is the equation v is equal to u plus at. And I can actually say, well, that's one of my SUVAT equations, derived from straightforwardly from dv by dt equals a, using a bit of integration. So, okay. That's kind of okay. I've got the first little bit. Now, the next thing I'm then going to do is go, well, actually, dv by dt, v is actually ds by dt, rate of change of displacement with respect to time. So ds by dt must be equal to u plus at. And I'm going to integrate those again. So what I'm going to get then, if I'm going to integrate this with respect to time, I'm going to get s is equal to u times t plus a half times a times t squared plus some form of constant. Now, I'm not going to take you through how to do it in terms of dy by dx the way that maths like to do it, but hopefully you can see how that works. So, all right, I've got that. Now, I know that at t is equal to 0, so at t is equal to 0, s is going to be 0. I haven't moved it, so my s is going to be 0. So therefore, I know that my c, my constant, is going to be 0. All right? So therefore, I'm now at the scenario where I've worked out my second SUVAT. Nice and straightforwardly. Now, to finish it off, though it doesn't actually involve integration, what I'm going to do then is just take v is equal to u plus at and say, well, actually, that means that v squared must be equal to u plus at all squared, and that has to be equal to u squared plus 2uat plus a squared t squared. So all I've done is expanded that out. I've times u plus at times by u plus at. U times u giving me u squared. At times by at giving me a squared t squared. And u times at twice over, giving me the middle term. So what I'm going to do then is just write, well, that's u squared. And here I've got a common factor, or a factor I'm going to pull out. I'm going to pull out 2a of these two terms. So that's going to give me, pull 2a out of there, gives me ut, pull out 2a out of here, I'm going to get a half times by a times by t squared. But hang on a minute, we just proved that ut plus a half a t squared is actually equal to s. So here I've got v squared is actually equal to u squared plus 2as, which again nicely gives me my third Suvat equation. Now, whilst this is all very useful and very good, I'm going to highlight one thing very clearly. You cannot use integration on an A-level physics paper. So you could not do this and expect to get any marks on an A-level physics paper. The whole point of the A-level specification is that you do not need to know how to integrate at this level in physics. Okay, it would be useful if you could, but that would mean you have to study A-level maths, and A-level maths is not a requirement for A-level physics. Okay, so hopefully for those of you who study maths, this is useful and you can see how it works. Certainly it made sense to me and I understood finally why I was being taught how to integrate and indeed differentiate in maths. Thank you very much.